Welcome back. So our next concept of this lesson has to do with the applications of acid-base reactions. How do we then apply them in our daily lives, in our everyday lives? Now, we know that we use acids and bases in many ways, and there are also economic uses of these chemical substances, that being now the acid and the base. We add bicarbonate of soda, which is now going to be our NaHCO3. So this is going to be our NaHCO with a subscript 3 there. We're adding this to bread dough or a cake mix, and we know that it's going to release the carbon dioxide. Remember, carbonate is going to release the CO2. Now, it is going to release the carbon dioxide gas, which makes the dough or makes rice. So we know that whenever we are baking at home, we normally leave the dough outside or leave it just for a few minutes for it to rise. That is because of that release of carbon dioxide, which is going to make the dough rise. We also know that most swimming pools have a careful controlled pH. We add a pool acid when we need to lower the pH. We add soda ash, which is now going to be our sodium carbonate. When we need to raise the pH. We know that in most cases we clean our swimming pools using the acid or using the base, depending on what you want to do. So we see now on this picture we have a before and after, before treating the pool and after treating the pool, how it looks like. So basically, as we have said, there are many uses of the acid-base reactions, and these ones are also economic uses, and we use them also in our daily lives, even at home. If you have a swimming pool, we know that when mom or dad cleans the swimming pool, they're going to be using the acid. Also, bee stings. I'm sure some of you have been stung by a bee. We know that they are very painful because bees, they inject an acid, which is they're injecting that acid under your skin. Then the bicarbonate of soda will help relieve the stinging because it neutralizes the acid. Remember, the bicarbonate, the carbonate, we have said that that's a base. So when a bee stings and injects an acid onto our skin or under our skin, we need a base to neutralize that acid. So we're going to be using our bicarbonate of soda. Now, we also know that the wasps, they sting also, and that sting is also painful. They inject a base under your skin, so it must be treated with a weak acid like vinegar. So bees, they inject an acid, whereas the wasp, they inject a base. So we know that to neutralize either the acid or the base, you need to use one or the other. If you want to neutralize an acid, you must use a base. If you want to neutralize a base, you must use an acid. So when the wasp injects the base under your skin, you need to use a weak acid, just like vinegar. We do know that vinegar is an acid. It's a weak acid because we can be able to consume it. We can be able to use it whenever we are cooking because it's weak. We can be able to ingest it. We also know that too much acid in the stomach causes indigestion and heartburn. So then we know that the antacids are a group of medicines that are used to neutralize the excess stomach acid. Whenever we have heartburn, we know that we drink some milk maybe to neutralize the acid that is in our stomach. So that is also an acid-base reaction. We are neutralizing the acid using a base. Now, typically they contain bases like calcium carbonate, magnesium carbonate, magnesium hydroxide, and aluminum hydroxide. So those antacids, they contain these particular bases. We have calcium carbonate, magnesium hydroxide, and aluminum oxide. Furthermore, the inside of the mouth, we do know that it's usually slightly acidic after a meal. So after you've eaten something, the inside of your mouth is going to be slightly acidic. And obviously, we wouldn't want your mouth to be acidic. So therefore, the acids can damage your tooth or the tooth enamel and lead to tooth decay. So therefore, we need to use something to neutralize that acidic substance in the inside of our mouth. So we normally use the toothpaste. Why? Because it is weakly basic, and it can leave the mouth slightly basic after brushing your teeth. So this is why it is very important for us to brush our teeth after we've eaten something, because we're trying to neutralize the acid that is inside our mouth by using a toothpaste that is weakly basic. Because we said if something is weakly basic, it has a pH that is greater than 7, but closer to 7, could be like 8 or 9, or maybe 7.1, 7.2. Those are still weak bases. Furthermore, most soils are slightly acidic. Most vegetables, they like acidic soils. And also, most flower crops grow better in neutral or basic soils. So therefore, farmers can use limestone to make soil less acidic. Because we have most flowers that they like neutral or basic soil, we can use the limestone to neutralize the soil that is slightly acidic. The chemical formula for the limestone is our calcium carbonate, which is CaCO3. And by adding a carbonate to the soil, the pH can be raised for crops that prefer a more basic soil. So by adding the limestone, which has a chemical formula of CaCO3, we are basically going to be raising the pH of the soil so that the flowers that prefer a more neutral or basic soil can be able to thrive and grow. So when we are now going on to our last concept of this lesson, whereby we'll be looking at the reactions of acid and metals, we need to know what is going to be the product of the reaction between the two, how do we name the product, and also what happens in the reaction. We first need to know that metals are very useful materials in a wide range of objects. Unfortunately, many metals react with acid when they are in contact with each other and can cause corrosion and damage. We know that whenever we have corrosion is basically the eating away of a material or even flesh. We know that the substances which are corrosive are bases and also the acids. They can be corrosive and can cause damage. So when a metal reacts with the acid, there's going to be corrosion that is taking place there. However, the reaction between an acid and a metal, it is going to be producing a salt and a hydrogen gas. So when that reaction between an acid and the metal occurs, the salt and hydrogen gas are going to be produced. We normally say that the reaction between an acid and a base produces a salt and water. In this particular case, the reaction between an acid and a metal is going to produce the salt and the hydrogen gas. Why do we not have the water anymore? The reason is the HCl, or the acid as our example, is going to be donating or contributing the hydrogen. However, the metal, as we can also use the magnesium, the HCl as our acid is going to be producing or donating the hydrogen, and then the metal that is in question here doesn't have any oxygen or doesn't have any hydroxide to produce or to give off or to donate. So therefore, there will not be any reaction between what was given off by the metal with what was given off by the acid. So therefore, the salt is going to be the remainder of the acid, which is your Cl, and the magnesium. So it's going to be magnesium and the chlorine. And then what was given off by the acid, being the hydrogen, is going to be only just that, the H2 gas. And also notice that the number of hydrogen atoms do not match. They are not the same. On the left-hand side, there's one. On the right-hand side, there's two. So on this reaction, we might need to balance the chemical reaction. We know that the acid, as we have said, the acid provides a non-metal part of the salt after having donated the hydrogen. This part combines with the metal part to form the salt product. Because the metal didn't have anything to produce, it is just going to be combining with the non-metal part of the acid to produce the salt, and the salt's name is going to be determined by the name of the acid and also the name of the metal that was in the reaction. Unlike the reactions with hydroxides or oxides, and even carbonates, there is no oxygen available from the reactant to form water. As we have said, we only have just the metal. There is no oxygen available to combine with the hydrogen that was given off by the acid so that the water can be formed. So for that reason, there's going to be only just the hydrogen that is going to be produced. So because instead, the acid loses the hydrogen atoms to form hydrogen gas. That is why we do not have the water produced by the reaction between an acid and the metal, because there's no oxygen, so we're just going to have the hydrogen. So then how do we then name the salt between the reaction of an acid and a metal? So we're going to have an acid, we're going to also have a metal. They are going to react together to form the salt plus the hydrogen gas. So the name of the salt, as you have said, it's dependent on the name of the metal and the acid. When we start with the hydrochloric acid as our acid reacting with potassium, the hydrochloric acid is going to produce or is going to donate the hydrogen, and then the remainder, the non-metal part of that acid, is going to chemically bond with the metal, being the potassium, to form potassium chloride. Same applies with calcium being the metal, sulfuric acid being the acid. The sulfuric acid, because it has the chemical formula of H2SO4, that H2 is going to be donated, and then the non-metal part being the sulfate, the SO4, is going to chemically bond with the calcium to form calcium sulfate. Same thing applies with nitric acid and ethanoic acid. The acids are going to be donating the hydrogen, and then the non-metal part that is being left over there as a remainder is going to bond with the metal to form the salt. So the name of the salt starts with the metal, and then the last part being the non-metal part that is coming from the acid. So in general, we're saying if we know the metal and also know the acid, we can be able to predict the name of the salt that is being formed, because we know that acid is going to donate hydrogen, then the remainder being the non-metal chemically bond with the metal to form the salt. The name of the salt starts with the metal, then the last part is going to be the non-metal coming from the acid. Then, a typical reaction, we can represent a typical reaction of what we're talking about using a word equation or even a chemical equation. For instance, sulfuric acid, as we know, it has a chemical formula of H2SO4. We can also have lithium as our metal, has a chemical formula of Li, capital letter L and small letter I. And then the salt being formed is going to be lithium sulfate. Remember, as we have said, we start with the metal. The metal doesn't give off anything because it doesn't have the hydroxide or even the oxygen to produce or to give off. Whereas the sulfuric acid will donate that hydrogen atom, and then it is going to be just that because it won't have anything else to chemically bond with. So the product that is going to be formed is going to be lithium sulfate, the Li chemically bonding with the sulfate to form the Li2SO4 and our hydrogen atom. And remember, because this is a reaction between an acid and a metal, we need to make sure that the number of atoms on either side of the left-hand side and the right-hand side, they are equal. So we need to balance the reaction. With this reaction, it was balanced by just inserting the 2 in front of the lithium. Because 2 lithium atoms, now I have 2 lithium atoms. Two hydrogen atoms, there were 2 hydrogen atoms to begin with. 1 sulfur atom, 4 oxygen atoms, and 4 oxygen atoms. So therefore, the reaction is balanced. We need to make sure that we always remember that whenever we are reacting an acid with a metal to produce the salt and the hydrogen, remember that the hydrogen is a diatomic molecule, so it exists as the H2, which is why you always need to make sure that those hydrogens on the right-hand side are equal to the number of hydrogens on the left-hand side, which is why we always need to make sure that the reaction is balanced. So learners, I hope you had as much fun as I did with this lesson, and until I see you next time. Bye.